Hi everyone and welcome to today's video on product rule with circular functions. Yes, I had to look down to try and remind myself what it is. Now, this is a continuation actually. It's the product rule with circular functions. Now, those of you who are being taught by me, you realize that we did the product rule a while ago, but we didn't do any of the circular function stuff. We left all of that to the end. And now we're here. Let's just go back and recap the product rule, but now with sine, cosine, and tangent. In case you're watching this video much later than I actually taught it, well, let's recap the basics of product rule and start with differentiation. Now, we know that if we have 3x squared, a basic term on its own, it's really easy to differentiate. That just becomes 6x. Nice and easy, multiply the power and the coefficient and take one off the power. But it becomes more complicated when we have more complicated terms. And while we can, in this situation, quite easily FOIL it, first, inside, outside, last, we can have other methods available to us. Now, yes, foiling this could be simpler than the product rule, but I'm going to use the product rule just as a basic introduction. So what is the product rule? It is the idea that we've got two x terms multiplied together, and by that I do not mean x times x to the power of 4. In that situation, we would simplify it quite simply and differentiate it as one term. We're looking at things that are slightly more complicated. So, with our question, taking rid of these two wobbly bits here, we know that the rule states is y equals uv dashed plus vu dashed. Now don't worry, there are lots of variations of this. And for example, y is equal to u times dv by dx plus v times du by dx is another way of writing it. I don't like it that way because, as you can see, it takes a lot longer than just to say y equals uv dashed plus vu dashed. But everywhere I see a dashed, I know that means to multiply by the differential of u or v. Which one is u or v? It's this one here. I'm just going to choose a u to be the first one and the v to be the second one. In the United Kingdom, if you're watching this, I know that probably things get a little bit more complicated, and there is, on occasion, an order you have to stick to, or you're not going to be able to do this particularly well. That's fine, but over here in Australia, it's nice and simple. So, having chosen my u as 2x squared plus 1, and my v as 4x cubed plus 12, well, it now says to differentiate it. So I've got u dashed is equal to 4x, and I get v dashed is equal to 12x squared. Now, the reason I do this, what I call breaking out, is the lovely thing is that actually opposite corners make up my product rule. What do you mean? Well, here's my u and my v dashed, and here is my v and my u dashed. So I just multiply those opposite corners together. So what do we have now? We know that y equals, or y dashed actually that should be, y dashed is equal to u, which is 2x squared plus 1, times v dashed, which is 12x squared, plus v, which is 4x cubed plus 12, times by u dashed, which is 4x. Wow, I didn't think I was going to have enough space there. Would I leave it this way? No, I have to multiply it out and collect like terms. So what do we get here? 2, so that would be 24x to the power of 4 plus 12x squared. Multiplying this out gives me 4, 12, 16x to the power of 4 plus 48x. We've got two terms in x to the power of 4, so I'm going to simplify that even further, which gives me 40x to the power of 4 plus 12x squared plus 48x. Now that was the process. In this situation, it might actually have been quicker to do my FOIL, first outside, inside, last, and then differentiate the individual terms, but not in this one. So if we go to my next example, and again, this is still just scaffolding product rule for those of you who haven't done it for a while, but are now coming back to circular functions. Not having a circular function question, but again, I've got an x term times an x term. So this is my u, and this is my v. So what I'm going to do is again write u equals x to the power of 4. So u dashed is 4x cubed. V is equal to 2x minus 6 to the power of 3. And v dashed is. Now in this situation, I could use binomial expansion. That would take at least another 20 minutes. But thankfully, I know the chain rule, which is nothing like a chain gang. Because no one would want to be on a chain gang. And those of you who don't know what the chain gang is, look it up. It was not a lot of fun. But v dashed is equal to 3 lots of 2x minus 6 squared. So when you remember, when you use the chain rule, same sort of principle with ordinary differentiation. Multiply the power and the coefficient, which is 1, take one off the power, but you then have to multiply by the differential of the bracket. which in that situation is 2. So v dash gives me 6 lots of 2x minus 6 all squared. I've done my u v dash. Now I do this every time. I don't try and do it in my head. I always do this bit of a breakout section. So now what do we have? We have y dashed is equal to u, which is x to the power of 4, times v dashed, which is 6 lots of 2x minus 6 squared, plus v, which is 2x minus 6 cubed, times u dashed, which is 4x to the power of 3. Now I don't leave it there because what I can see is in methods and all subjects pretty much around the world, you have to actually write it in the simplest form. And I can actually see that I have 2 terms here that can be factorized. Yeah, so what I'm going to do is take out the most. First things I do is look at the constants, and I've got a 6 and a 4. Most can come out of that is 2. I've got an x to the power of 4 and an x to the power of 3. So the highest that can come out of there is x to the power of 3. And these brackets, remember, say treat me like one thing. And I've got 2 things in one of those terms and 3 things in another. So I can take out 2x minus 6 squared from all of those individual terms. Now I write square brackets here so I don't get confused with curved brackets everywhere. But when I take out 2x cubed, I get 3x out of my first term. And I'm going to add, and I'm going to take out, well, 2 out of that one, but in this situation, 2x minus 6. And there's why I do my square brackets, so that I don't have curved brackets inside curved brackets. Right, that stays the same because I can now simplify inside my bracket. Still staying with a square bracket, just so that I can do this. Oh, no, 2 times 2 is actually 4, and I'm going to take away 12. And so, nice and simple. 2x minus 6 all squared. Now I'm going to use my curved brackets to give me 7x minus 12. And I think that's probably nicer and quicker and more beautiful for mathematics, because we love a little bit of beauty in mathematics. Yes, I know, beautiful, fabulous. To help me differentiate that function, which if I had to try and multiply that out using, binomial products and factors and then try and factorize it all back together, would be horrific. And that video in itself would be an hour long. So we've now got to the point where we can actually use my circular functions. Now, the great thing about methods in Australia is that circular functions is not a particularly massive section in terms of what we have to be able to do, so long as we can remember the following table. So here is my y and here is my y dash. And I know that sine of theta goes to cosine of theta. I know that cosine of theta goes to the negative sine of theta. And I know that tan theta goes to sec squared theta. Now, if you don't remember why, go back and watch my previous video. It's, again, I mean, I'm biased. It's brilliant. It's just the best video in the world. But the reason I always write this table is because I remember that actually for differentiation and integration, it's really useful because I can, if I know I'm differentiating one way, I know that I can integrate the other way. Yep, because we're going to differentiate that way and then we can integrate the reverse way. But that's rushing ahead. So we've got to differentiate. We've got y is equal to 2x squared times the sine of 2x. Can't simplify that into one nice beautiful term that can be differentiated, so I've got to use my product rule. What do? We choose u and we choose v. So let's do my u is equal to 2x squared. My v is equal to the sine of 2x. U dashed is 4 of x. Now v dashed. This is where I'm now going to have to use my chain rule. And again, that's slightly beyond what this video is about. But I know that sine of 2x goes to the cosine of 2x. And I know that I then would multiply that by the differential of that 2x, which is 2. Again, if you don't remember how to do that, go back. Chain rule is brilliant and used so much in mathematics. But for the purposes I've got now, I've got my u and my v dashed and my v and my u dashed. So using that y dashed is u v dashed plus v u dashed, I get y dashed is equal to u, 2x squared, times v dashed, which is 2 lots of cosine of 2 of x, plus v, which is the sine of 2x, times u dashed, which is 4x. Now, please do not think that that becomes the sine of 8x squared. Nah. This sine of 2x is one term. So I'm going to rub that out completely and go, ugh. Simplifying this gives me, that I can simplify to 4x squared times the cosine of 2x, plus 4x times the sine of 2x. Now, in this situation, I wouldn't factorize anything out because there's nothing really to factorize out. Yes, I could write 4x outside a set of brackets, which would leave me as x times cos of 2x plus the sine of 2x. But to be perfectly honest with you, I don't think that aids the readability. I don't see the advantage between the two of those of actually doing it. Now, there's not too many examples I can do here, but so long as you remember that sine goes to cos and cos goes to minus sine and tan goes to sec squared, then pretty much the rest of it's all there. Just recap. Make sure you know how to go and use the chain rule with circular functions as well. But the product rule is just funky. Right, thank you very much for taking your time in watching this relatively short video. It's been good having you. If you'd like, please, please, please subscribe to my channel so that you can see when new videos are created. If not, watch another video that's over there. Now, I'm on Patreon. So excited. If you feel like helping me create more videos, then please, please, please go to the link below. Go to the link below. Go to the link below. But otherwise, if not, hey, I won't hold it against you. It's been good seeing you. Thanks so much. I'll see you again.